Hello everybody, this is Calculus Casual, and today I'm going to show you some basic derivatives. Now, last lecture, what I went over was mainly just what the derivative was, how to take the limit to find the derivative, but today I'm just going to kind of show you some more derivatives without without giving you an explanation, and then some other ones that I do derive, but then the rest I'll leave up to you. Before I get into the more specific stuff, I'm just going to go over some general rules that'll prove to be a lot more useful when you actually um, when you're actually doing it in real life. All right, probably the first rule I should mention is something we call the chain rule, right? Now, basically what this means is if I have some function, right, f of x, right, actually f of another function called g of x, right, f of g of x. And I'm going to take the derivative. Now, actually, a popular notation we have for this derivative, if I could just keep this editor working, is prime, right? So this prime symbol means that this is a derivative I have right here, right? So this f of x, g of x, I'm trying to take the derivative of f of g of x, right? So what is the derivative of that? What is the derivative of a function of another function? Well, as it turns out, that's f prime of g of x times g prime of x. Now, the derivation of this mainly involves limits, I believe. It's just rearranging of limit terms, if I'm not mistaken, to get these expressions, but I'm not going to go over that. It's a little bit more involved than some of these ones I'm about to show you. But yeah, I'll just set that up as a challenge to you to figure out what that is. But I'm going to explain some other derivations that basically rely on these ones, right? So, I mean, in math, we have all sorts of interdependencies. Like, in order to prove this is true, we have to prove something else about calculus, or in order to prove that, um, yeah, you'll see what I mean later on. But anyways, yeah, that's what we call the chain rule. Now, one example of the chain rule's application would be something like x plus 1 squared. Now, this is a very simple example, right? We could just go ahead and multiply this out, and we'd see what the answer was. Now, if I use a chain rule, what I would do is I would say, okay, well, x plus 1 squared, well, let's say f of x equals, well, that's not technically true. Let's just say that f of x equals x squared, and g of x equals x plus 1. So this is f of g of x right here, right? Because x plus 1 squared, quantity squared, as some people say for some reason. So in order to evaluate this, what do we do? Well, we apply what we call our chain rule. Actually, we need to say that this is the derivative we're trying to take, right? So then we say prime, right? We say d this over dx. It's just another way of saying the derivative, right? There's a lot of, the editor's giving me some trouble here. Over dx. Yeah, that's basically what it is, right? So the derivative, right? Derivative of this. What is the derivative of this? All right, so chain rule, right? I'm going to pause the video and try to figure out what this is. All right, so according to our substitutions, this is g of x, right? X plus 1. F of x is x squared. So f prime, the prime value of f of g of x, right? The derivative of f of g of x would be f prime of g of x, right? So derivative of the outside, right? We take the derivative of the outside. So that's 2 times x plus 1 according to something we call the power rule. Actually, I haven't went over that yet. Basically, I actually think I challenged you to figure this one out the previous lecture, but just in case you didn't get that, we have a function like y equals x to the nth power. Um, then y prime, that is the derivative of y, equals n times x to the nth minus 1 power, right? So we reduce the power by 1, and we multiply it by that value, right? Now, something that happens is, like, if you have a function like y equals 1, then y prime would equal 1 to the, now, notice that 1 is x to the 0th power, right? So it's just 0 times 1 to the negative 1 power, which is 0, right? Because 0 times 1, I mean 0 times anything, virtually anything, right? Except for infinity, but that's kind of confusing. And anyways, I'm getting sidetracked here. So, yeah, this is the power rule, right? You can generalize it, and it's very essential to calculus, just like this is, and like many other things are. But anyways, so right, I got sidetracked. So, right, that's the derivative of this function. I believe it or not, actually, I believe we're done here, right? Because the derivative of this, what's inside, right? Then we need to multiply this by, according to our chain rule, right? Derivative of x plus 1 is just 1. So we multiply this by 1, and that's what we get, right? Which is equal, this whole thing is equal to 2x plus 2. Now, if you multiply, and notice if you factor this out, you get the same result, right? And if you, not factor it out, it's already factored. If you multiply it out, right? Reverse operation of factoring, you'll get x squared plus 2x plus 1. And if you derive that, I mean, if you take the derivative of that, right, by the chain rule, the derivative of x squared is the power, right, which is 2 times x to the 2 minus 1th power, which is 1, right? So 2x plus 2 plus 0, because the derivative of 1 is 0, right? And the derivative of 2x is 2, because, I mean, just intuitively, right, if we have a slope of a function y equals m times x, then our slope is m. So yes, this is the value of our derivative, right? Which, as you can see, matches this value right here, right? But this, I mean, overall was easier. I mean, okay, maybe it didn't seem that much easier, but like, there's many examples where this chain rule is the only thing that we can do. I'm not necessarily go over those this time, but hopefully you understand what this means, and it's, hopefully you understand what this means. So, anyways, yeah. So basically, what I'm saying is, if I have rate of change of one function of another function, then that rate of change will be equal to the rate of change of that first function, right? The value of that function times the rate of change of the other function. It's kind of intuitive-ish, but you do kind of have to, have it told to you or see an example for it to, for you to really know it for sure is the truth. But anyways, moving on from there, that's just one right there. The chain rule, that's very important. I mean, that is essential to derivative calculus. But moving on to that, another one we have that I'm not necessarily going to prove is y equals, let's see, cx. Y prime will equal c, right? I mean, you kind of already know that, because c is a constant, right? Now, if we have a constant times x, we have like a y equals mx plus b type equation. In this case, b equals 0, could equal any value. But you see that the derivative is a slope, so the derivative is m, right? You could just as easily say that y equals mx, y prime will equal m, which is a slope, so which really kind of clarifies things for us. Anyways, that one's intuitive. And one is if y equals f of x plus g of x, then y prime, if I'm not mistaken, actually, yeah, y prime would equal f prime of x plus g prime of x. It's basically the sum rule, but with derivatives. Now, if this is wrong, please let me know. I might have explained this badly, this particular part right here, but hopefully it's intuitive to you anyways. So, moving on from that, let's see, another one. Yes, this is another one that's essential, that I should mention, is if you have a function y equals f of x times g of x, then y prime equals f prime of x times g of x plus g prime of x times f of x, right? So there's kind of a crisscross thing going on here, right? I mean, it kind of think it might remind you from something from trigonometry, if you remember trigonometry well. I don't, but um, yeah. So I mean, this might be kind of a familiar arrangement, right? So anyways, yeah. So an example, well, let's just say y equals x times x, right? We already know the derivative of this is 2x, but let's just try deriving it this way, right? Derivative of x is 1, right? So x times the derivative of x is x plus, I mean, you could reverse the order, but it doesn't really matter. You have the same thing, right? Because x times x is just x plus x, which equals 2x, which we already know because of the power rule. But hopefully this clarifies those things and kind of connects them in your mind a little bit better. Anyways, moving on from this, let's see here. So there's a technique called implicit differentiation, but hopefully just, in general, like reasoning and some intuition should kind of tell you that it's true. So I'm not going to go over like what it means right now. But it is relevant to what our how our derivations for these other functions work. Okay, so anyways, have you all ever heard of the number e? And you probably have, right? In pre-calculus, e is the limit of 1 plus 1 over x as x. I mean, let's see, 1 over x, 1 plus 1 over x to the power of x as x approaches infinity, right? So I mean, that's what he is. I'm not going to dwell upon that too much because, frankly, I can't say that I fully understand it myself or I'm qualified to explain it. I'm not qualified to explain anything, I suppose, but this is, if you understand this, and I say you're a pretty qualified, smart person. Anyways, I mean, I'm not saying specifically about, I mean, I'm not saying I understand this, right? I don't, right? So that's my point, right? If you understand this, then good for you. Congratulations. So, yeah, moving on from that, another special thing about E, another definition I can make for E is that the derivative of e to the x is e to the x. So, yeah. Now, according to our chain rule, if we have a constant like e to the c of x, if it's e to the c of x, well, we use a chain rule, right? We could do e to c times x, but then we also have to multiply that by our derivative of cx, which is c, right? Just multiply by the derivative of what's inside. And my apologies, this is not cooperating right now. Okay, yes, e to the c of x times c, right? I mean that's derivative. Hopefully you see that from the chain rule. But anyways, yeah. So moving on to derivations, right? This tells us something kind of special, right? Now let's just go over this math discovery together, right? Now this is one thing we know, right? The derivative of e of x is e to the x. So using that fact, okay, let's let y equal log of x, okay? Bear with me here, right? Let's just say y equals log of x, right? And I want to find what y prime is. Now, I could just directly try to derive that, but actually I can't unless I know what the derivative of this is, right? I mean, I could try to take the limit, but if you try to do that, I think it's kind of complicated, so I'm not going to do that. Instead, I'm gonna use this thing we call implicit differentiation. But before I do that, I'm gonna do a little bit of a rearrangement, kind of restatement of this problem here. So let's just raise both sides of this equation to y. We take ln x. I mean, not to y. What am I saying? We raise e to this side of the equation power, right? So that's e to the y equals e to the ln x, right? That makes sense, right? Hopefully you kind of understand that. So, yeah. So we know what the derivative of e to the y is, right? But we also know what e to the ln x is. It's just 1, right? I mean, it's just x, right? So we have e to the y equals 1, right? That is correct, right? No, equals x. I'm sorry, equals x, right? E to the y equals x, right? And that's kind of what our logarithm is, right? So we applied our inverse function, right, to this, and it gave us this. And now what we can do is we can differentiate this because we know what the derivative of e to the anything is, right? It's e to the y. Now we could say the derivative, taking the derivative of both sides. Now here's what's important to remember is that the derivative of e to the y is not just e to the y, right? Because y is a function. We have to use the chain rule, and we have to multiply this by the derivative of what's inside, which is y. So we take y prime times e to the y equals 1, right? Because the derivative of x is 1, right? Now, if you divide both sides by e to the y, what you get is 1 over e to the y. Now, what is y? Now, if you recall, think back, y was actually ln x. So e to the ln x is x. So this ultimately means is that the derivative of our function, which is ln x, is 1 over x. So that's just one example, right? That's just one example of what we just did is we derived derivative, right? I'm not going to go over all the examples of specific, functions that are, mixtures of different like I'm gonna go over these basics right here, so that way, like you all see these derivations, and hopefully they'll help you. Um, yeah, I challenge you to try to derive the other ones like the chain rule and everything. I mean, that's a little bit harder. Anyways, yeah, moving on from that. Um, so this derivative, right, y equals e to the x, actually opens up more than just this to us, though. So now that we know the derivative of ln x is, which is we know is 1 over x, right? We can actually do more with that. So let's say we have a function y equals, let's see here. It's a good example. Maybe log a. Oh boy. Log a to, log ax, right? You want to know how we take the derivative of x's logarithm, right? I'm going to figure that out. So, yeah, in base a. Now, something we know is, I believe this is correct. Let me look this up really quickly because I don't remember. Again, I don't claim to have any professional certification. I'm just a calculus student trying to figure things out. So, see, ln x, um, logarithm identity. See what that is. Some calculus. Let's see here. Okay, yeah. Log ax equals log x divided by log a. Okay, that's our identity here. Now, log actually in this context right here is just ln, right? So ln x over ln a. So we can apply that identity back here, here. Let's see that again. I forgot immediately. Ln x over ln a. Okay, so that's ln x over ln a, right? We know this from our pre-calculus derivative or identity or whatever. So we know that now, right? And what else can we do? Well, let's see here. So we know our chain rule, right? We could go over the dividing rule, but I really don't think it's worth it. I mean, really, it's just really the multiplication rule would do it for you. I think a lot of even calculus professors forget whether ratio rule is or whatever. I'm not going to go over that. Or its derivation. Really, you just need the product rule. You don't need the product rule and that other one. So, anyways, yeah. So you could say that this is y equals ln x times 1 over ln a. right? Now, 1 over ln a, notice, is a constant, right? So this is really easy for us. We know the derivative of ln x is just 1 over x. We know this constant just stays there. So now it's 1 over ln a. Well, actually, I forgot to take the derivative here, right? Because I took the derivative, right? That's what I just did, is I took the derivative, right? So the derivative of ln x is 1 over x, and the derivative of 1 over ln a, well, since I'm multiplying, right, that I just keep that. And this is what I end up with, y prime equals 1 over x ln a, right? So basically, this means that, right, if I have a function like log a x, right, base a, and then thing value x, right, then the derivative of that is going to be 1 over x ln a, right? Okay, so yeah, hopefully that's clear to you. This one. Another derivation, you don't have to memorize these. It's really just, I think it's helpful to be able to do them. Again, if you need to, whenever you need to, but I don't see it as essential, right, to knowing calculus. I just see this as useful, right? I mean, I want to say this video is essential either, right? None of my videos are essential. Videos are essential, right? You could watch somebody else, but I'm here. I could help you out maybe. So, anyways, yeah, I mean, you know that already. So, let's see, what's another example? Well, another function you can apply this to. Let's see here. So another good one would be y equals a to the x power. I'm sorry, a to the x power, right? Y equals a to the x power. So, um, well, let's see here. So what can we do here? Well, we can apply what we just know, right? We know what log a to the log a x is, right? We know the derivative of that is, I'm sorry, I keep forgetting to put these primes here. The derivative of log a to x is 1 over x ln a. So, anyways, yes, y equals a to x, right? What do we do? Well, if you want to find the derivative of that, let's just take log a of both sides, right? So log a y equals log a to the x, this is x, right? So log a y equals x, right? Now, if I take the derivative of both sides, well, what do I get? Well, on the left side, I get 1 over, let's see, y ln a times the derivative of y, which is just y prime. So y prime over y ln a equals 1, right? Because the derivative of x is 1. Now I can multiply both sides by y ln a, and I get y prime equals y ln a, which is equal to, remember what y is, y equals a to the x, so it's ln a times a to the x. Now notice there's kind of a significance here, is that you keep taking the derivative of a to the x, and you would keep getting just this constant, right, ln a times a to the x, and that's significant later on, but I guess, it's worth maybe dually noting here, but yeah. Anyways, yeah. So those are a few examples, right? Many other derivatives can be derived in a like manner, right? You really see the gist of what we did here is if we knew the inverse of a function, we knew some identity that related that function to another function, that we could derive its derivative through implicit differentiation. But then derivatives you have to derive directly are a little bit more complicated, especially these really general ones, they involve other operations that, are a little bit, some of them are a little bit above my scope, I think. But anyways, though, I challenge you to go out and look for that. I think stuff like the, you know, multiplication rule. I think it's pretty simple to understand, but I'm not going to carry out the operations here because it takes a lot of, I mean, it doesn't take a lot of paper because I'm doing this digitally, but it takes a lot of space, and I just figure, like, well, it'll be a challenge, right? It'll be a challenge for you. I mean, for me right here, it's just kind of like I don't remember exactly how that derivation goes, so I'll just look up some documentation for it. But yeah, those are a few examples. So anyways, though, I guess that ends it for this video. Hope you all enjoyed it. Hope you all thought it was at least mildly entertaining for a calculus video. Hope you all have a wonderful, blessed day. and I guess I'll see you next time.